Great. So hey everyone, welcome back to our fifth session now. So before we move on to our next topic, I just want to really quickly revisit this concept of cross-validation since many of you found it a bit confusing yesterday. So usually when we build a model, we divide our data set into two parts. So we have one that our model is going to be learning from, which is our training data. And then we have another to test how well the model would perform on new unseen data, which would be the test data. But I mentioned yesterday that if we only use one split, our results may be overly optimistic or over pessimistic just by chance. So cross-validation allows us to address this by repeatedly splitting the data into training and testing sets, and these are things called folds. And this process really helps us get a more reliable estimate of how well our model would perform on unseen data. So this concept here, as shown in the outer loop, is what we were talking about yesterday, where rather than just having one train test split, we're doing it across multiple folds, and each part of the data gets an opportunity to be the testing set. Okay, that's one concept, but we've also talked about hyperparameters. And if you remember, hyperparameters are these, so we have settings chosen for before training that influence how our models performed. So we're able to choose the best hyperparameter based solely on the training data, and this can make our model specifically, we're choosing these K parameters within the training data because we don't want to overfit our data. So we're doing this specifically within the training set. So to avoid this, we're doing cross-validation to find hyperparameters that work based on different parts of the data. So the idea here is that we're taking the training data, we're creating a subset of training and validation, and we're iterating through different values of our hyperparameters. This would be known as the inner part of the loop. So there's outer loop for cross-validation and inner loop for cross-validation. In class, we looked at these concepts separately just to keep things simple. But in reality and practice, they often are combined, and this is a method known as nested cross-validation. Once again, this concept of nested cross-validation goes beyond the scope of this module, so we looked at these two things separately just for simplicity. But this is sort of what's happening just to better get your head wrapped around it. Does that make sense to everyone? Okay, I see thumbs up, which is great. Okay, cool. Oops. Okay, now we can move on to today's material. So up until this point, we've really focused on supervised learning techniques. So like classification, regression, where we're predicting a response variable based on predictor variables. And these methods, once again, rely on labeled data, meaning that we already know the outcome. So we already know whether something is a benign tumor or malignant tumor, or we already know the continuous value, for example, the price of the house that we're trying to predict. But today, what we're doing is we're shifting gears a bit and exploring clustering. And clustering is an unsupervised learning technique. And in clustering, we work with data where our response variable is not provided. And our goal is basically to group similar observations together based on their shared features. So for today's class, our learning objectives are the following. We're going to be learning when clustering techniques are useful, especially when we want to group similar data points but don't have these sort of predefined labels for our data. And this is especially useful for discovering patterns or gaining insights from unlabeled data. We're also going to dive into how K-means algorithm works to partition our data into clusters, focusing on its key steps, such as choosing the number of clusters, or known as K, iterating over data to assign points to the nearest cluster, and then updating the cluster centers. If this doesn't make sense to you, don't worry, we're going to get into it in a bit. And then, as I briefly mentioned, clustering is known as an unsupervised learning technique. So unlike classification, unlike regression, which are supervised learning methods. So we're going to go more in depth regarding understanding how supervised and unsupervised techniques differ, especially in terms of the data that they require and the tasks that they aim to solve. We're also going to get more hands-on practice, what K-means algorithms specifically, using scikit-learn and Python in the second half of today's class, and applying clustering to real data sets. We're going to explore how we can use the elbow method, which is a technique to determine the ideal number of clusters for our data by simply plotting them. And then lastly, after clustering our data, we're going to discuss how to interpret results, visualize the clusters, really make it easier to understand grouping and the patterns that we find within our algorithms. Okay, so clustering is the process of separating data into distinct subgroups or clusters, where data points within each group are more similar to each other than to other groups. And the goal is to uncover hidden patterns or structure in the data without predefined labels or categories. And some practical examples of clustering include things like grouping documents by topic. So for example, clustering can be used to automatically group documents or articles by their content. So for example, news stories in one category, research papers in the other, into these clusters representing similar topics or themes. In genomics, clustering is often used to help researchers group individuals based on their genetic traits and allow them to identify subpopulations with shared ancestry or genetic markers. In marketing, clustering can be applied to customer data to group customers based on their shopping habits. And this allows for businesses to target each group with tailored marketing strategies. So overall, clustering is often used in the early stages of data analysis to explore the underlying structure of our data. And by applying clustering techniques, we could discover this hidden structure, identify patterns, and gain insights into the relationships between different data points. So it's a really powerful tool to uncover the natural groupings that we have within our data when we don't have these predefined labels to guide us. So I already alluded to some of these differences a little while ago, but just to reiterate and go more into detail, clustering is an unsupervised learning task. And what this means is that we don't have a predefined response variable or label within our data. So the algorithm groups the data into clusters just based on similarity without any guidance from labels or outcomes. In contrast, we already have gone through classification and regression tasks, and these are supervised learning tasks. So here, the goal would be to predict a specific response variable, whether it be a categorical label for classification or a numeric value for regression, based on prior data or past data. And these tasks rely on label data to train the model, and then the model is evaluated on its ability to predict outcomes on the new unseen data, just as we've done up until this point. So one really clear advantage of clustering is the fact that it doesn't need labeled data. So since clustering is unsupervised, it doesn't require us to have labeled data to function, which could be a huge advantage when labels are either expensive or time consuming to get. So for instance, consider a medical diagnosis with a complex condition like Alzheimer's disease, let's say. Diagnosing Alzheimer's disease often involves specialists, extensive cognitive and biomarker testing, advanced imaging techniques, all of which can be costly, it can be resource intensive. So clustering algorithms can address this challenge by simply grouping patients based on their similarities in things like cognitive test scores or genetic markers or imaging data without requiring confirmed diagnostic labels. And these clusters could do things like identify individuals that may show early signs of Alzheimer's or specific patterns indicative of pre-diagnosis stages, enabling earlier interventions. Another clear advantage of clustering is its exploratory nature. So clustering can reveal underlying patterns, natural groupings within the data, making it a really valuable tool for exploratory data analysis when you're really not sure what to expect from the data. So once again, going back to this Alzheimer's disease example, clustering may reveal specific subtypes of Alzheimer's disease that were not predefined, helping researchers understand potentially various mechanisms underlying its progression or treatment response profiles across patients. So it does have these clear advantages, but it also does come with some disadvantages because there's really no straightforward evaluation method. So we talked about in classification and regression, clustering, they have these clear performance metric evaluation. Clustering doesn't have really a direct performance metric. So you can't just compare the predicted label to the true label to assess precision, for example, because we don't have a label. So without labeled data, it's really difficult to evaluate really how well the model's performing. So to assess clustering quality, we often rely on data visualization by simply just plotting the data points and their clusters, and then we visually inspect how well the clusters make sense to us. However, this approach is more effective with lower dimensional data like 2 or 3 predictors, whereas for high dimensional data, more sophisticated methods are required to really evaluate clusters effectively. So when evaluating clusters in more complex fields, experts or domain knowledge can assess whether the clusters make biological or clinically relevant sense or practical sense. So this is when you need some sort of expertise to sort of pull out their practicality. So what I mean by that is, for example, clusters in brain imaging data might be validated, for instance, by neuroscientists that are able to check whether they align with the known brain regions or disease mechanisms, for example. So we can consider a real world example to better emphasize these distinctions. So imagine you have a data set of lung scans and you don't know which ones are signs of cancer. So clustering can allow us to group these scans based on similar features, like unusual spots or patterns that may be associated with cancer. And this approach would help us to identify scans that maybe are exhibiting unusual characteristics, which may warrant further investigation, even without knowing what cancer specifically looks like within these scans. And this is especially useful for exploratory analysis where we don't yet know what the correct label is. On the flip side, imagine that you already know which scans are cancerous and which are not. In this particular case, you would apply something like a classification to train a model that will automatically label a new scan as either cancerous or not cancerous. So the model uses known examples based on label data to learn patterns associated with each class, and then it would be able to make predictions based on the new unseen scans. So that's a practical example of the difference between clustering and classification based on whether or not we have labeled data. Does anyone have any questions about this? Okay, I got thumbs up, so I think we're okay to continue. All right, so in this particular module, we're going to be focusing on k-means clustering, but it's important to note that there are several other clustering techniques used in data analysis that we're not going to cover in this particular module. So some common ones include things like hierarchical clustering, and this method builds trees of clusters, and it can either combine smaller groups into one bigger one or split big groups into smaller ones, helping you see the relationships between clusters in a hierarchical fashion. There's also principal component analysis, or PCA, and it's mostly used as a data reduction method, so to reduce the number of variables in the data. But it can also help you group data by highlighting important features. However, k-means is one of the most popular methods for grouping data into clusters. And really the goal of k-means is to make each group as tight as possible. So in other words, the goal is to minimize the within cluster sum of square distances, meaning that the data points in each group are very similar to one another while making the groups themselves as far as possible from each other. We're going to go into more detail about how k-means accomplishes this in the next couple of slides. Okay, so we're going to be working with the Polymer Penguins dataset and exploring how k-means works. In this particular dataset, we have 18 observations, so each data point represents one penguin. And the dataset contains two main features. The first one's the bill length, which is the length of the penguin's bill or its beak. And then the second one is the flipper length, which represents the length of the penguin's flippers. And our goal is to apply k-means clustering to this data set and see if we can identify distinct types of penguins based on these two features. So we use the two features, so bill length and flipper length, to group penguins and uncover natural clusterings that may exist within our data. So as I mentioned, data visualization is a really incredibly useful tool for understanding data, especially when you're working with small number of variables or features. So for instance, we could plot the bill and the flipper length of our penguins, and we may already start to see some patterns or groupings that emerge naturally just through visualization. However, while visualization does help us get a sense of the data, it becomes less effective as the number of variables increase. So imagine trying to plot more than 2 or 3 variables in a graph. It gets really tricky quite fast. So the more dimensions or the more variables we have to consider, the harder it is to spot these clear patterns just through visualization. And so to more rigorously group data and determine the optimal number of clusterings or groupings, this is when we need these clustering algorithms like k-means. So k-means is able to handle this task in a more automated way by analyzing the data and separating it into distinct groups based on characteristics. And this provides us with a systematic and repeatable way to identify clusters within our data, which would especially be important as the data set grows in complexity with these increased features. Okay, so just taking a look at the relationship between bill length and flipper length. So here we have flipper length on the x-axis, bill length on the y-axis, and we're just simply visualizing the data. We already start to see some distinct patterns. So just by the plot, it sees that there's 3 possible subtypes of penguins. So we have this first group shown in yellow. They seem to have smaller flipper length, smaller bill length. We also see the second group shown in blue. They have still a small flipper length, but larger bill length. And then we have this third group shown in red here, and they seem to have a larger flipper length and bill length. So the visual observation is the first step. But in order to confirm these groups and determine if they're meaningful, this is when these clustering algorithms like k-means come into play to help us verify if these subtypes truly exist or if we're just seeing this pattern simply by chance. So k-means, as I mentioned, is this algorithm that divides a collection of data into k clusters. So here k is this hyperparameter that we can modify. And the goal is to group similar items together such that those items within the same group are as alike as possible and the items in different groups are as different as possible. So to break this down with a really simple example, imagine you have or you're organizing a collection of different fruits into baskets. So just a few numeric characteristics. So for example, these fruits have different weights in grams. They also have different sweetness measured on a scale of 1 to 10, let's say. So at first, you don't know which fruit belongs together, so you just randomly place a few fruits in each basket. This is your starting point, it's just a guess. And now you're starting to check the fruits and if they do fit into the right baskets. So for example, apples may be light and sweet, but they're in the same basket as oranges, and oranges may be heavier and less sweet. So apples may actually fit better with pears, so you move them into their own basket. So each basket has something called a centroid, which is like the average fruit for that group. And the centroid starts off randomly, but as you move the fruits around, it gets updated. So the centroid, once again, is this average of all the fruits within the basket. So for all the features we're sorting on. So the centroid would be the average based on weight and sweetness. And you repeat this process of reassigning fruits into baskets based on their characteristics and updating this average fruit for each basket. And you keep doing this until the fruits are grouped well and the centroid stops changing. And if all the fruits in the basket are as similar to the centroid as possible, your grouping's good. But how do you really know you've done a good job at organizing these fruits? And the trick here is to measure the within cluster sum of square distance, or also known as inertia. And inertia measures basically how similar the fruits in the baskets are to the most typical fruit, so the centroid. And the smaller the inertia, the better the grouping. So if the groups are really similar to the centroid or to the average fruit in the basket, the inertia would be low and the grouping would be of high quality. If the groups are far from this, the fruits are far from the centroid, the inertia is high, suggesting that the grouping could still be improved. And the k-means algorithm automatically repeats this process, moving the fruits around between baskets, updating the centroid or the average fruit, refining the groups until the inertia is minimized and the groupings can't be improved any further. So that's sort of the idea. What mathematical method are you using to standardize the data before plotting? Are you referring to this plot here?
Yes.
Yeah, so we'll get into it in the live coding, but we just use the standard scaler typically. Okay, so I mentioned this idea of cluster centers or centroids, which would represent the most typical fruit. And to calculate the cluster centers or the centroids, you typically follow these steps. So for each data point in the cluster, it has two or more features. So let's say it has an X variable and it has a Y variable. So for each feature of X and Y, you calculate the average or the mean of the values of that particular feature for all the data points within the cluster. So for example, let's say you had a cluster containing 4 observations and you have 2 variables. You have your X variable and your Y variable. To compute the coordinates of the centroid, you would simply compute the mean of all the X's and the mean of all the Y's. And this would give you the coordinates of the centroid or the cluster center in this two-dimensional space of X and Y. Going back to this fruit analogy, imagine you're organizing these fruits into baskets and we have these two characteristics. So let's say weight would be X and sweetness is Y. If you have 4 apples in a basket, each apple has their own weight and own sweetness rating. Now, if you would want to find the centroid of the apples in the basket, meaning that you want to find the most typical apple in terms of weight and sweetness, this would represent all of the apples in the basket. So you just take the average weight and the average sweetness. And once again, that would represent the most typical apple in your feature space or the centroid. So once you have a centroid, you need to measure how far each data point is from the centroid. And this is a really important step because it tells you how tightly grouped the data points are around the centroid. So for example, in our fruit example, we want to know how far each fruit is from the centroid, the one we defined as most typical. In this penguin example here, we see in this figure on the right, we have a cluster of penguins, and each penguin has a flipper length and a bill length. And we have this centroid representing the most typical or average flipper and bill length for the penguins within this blue cluster. So the lines in this figure represent the distance between each individual penguin from the centroid. So this is a distance between this penguin and the centroid, this penguin and the centroid, etc. In other words, it's showing you how far apart each penguin's characteristics, so the flipper and the bill length, are from the average characteristics within the group. So if a penguin's flipper and bill lengths are very close to the centroid, the line would be very short. And this means that the penguin is very similar to the typical penguin within that cluster. If the penguin is really far from the centroid, like this one over here, the line would be longer, indicating that the penguin is different from the average penguin within that cluster. So the distance between each data point, so here each penguin and the centroid, is important because it tells us how well the data has been grouped. So the closer the penguins are to the centroid, the more tight the cluster is and the more meaningful it is. But if the penguins have these long lines, the cluster might not be a good fit, and the algorithm may need to adjust itself and the groupings to improve them. So you might be asking yourself, how do we actually define this distance? So I said the distance from this one penguin to the centroid. So in k-means clustering, distance is typically defined by Euclidean distance formula, which is the straight line distance between the two data points in feature space. And this might sound familiar to you, and this is because this is the same way that we calculate distance within k and n, so very similar. So once we compute the distance for each data point to the centroid, we basically sum up the squared values of each of these distances for all the data points within the cluster. And then we square these differences to get rid of non-negative or to get rid of negative numbers, making larger differences even more important. And this process is what's known as within cluster sum of square distance or inertia. So this WSSD just stands for within cluster sum of square distance. It's also called inertia once again. Yeah, so someone in the chat asked is a real value selected to be a centroid or is it a result of a calculation? So once again, just to reiterate, a centroid is basically the average flipper length and bill length of these 4 penguins. So we have penguin 1, 2, 3, 4. We're taking the average bill length and flipper length, and that's what's defining our centroid. Does anyone else have any other questions about this? Yep.
So yeah, so this model is based on the assumption that we already have clusters, right? But
Yes.
what if the clusters, the one which we are starting with, are not right? You know?
Yep. Yep. So we always start with a random start. I'm going to get into that in just a second.
Okay.
Yep.
Okay.
Great question, though. Okay. So as I mentioned, a larger within cluster sum of square distance indicates that the data points in the cluster are far away from the cluster center or the centroid, meaning that the clusters are more spread out. And this suggests that the grouping isn't tight and cohesive, and the quality of the clustering may not be the best. On the flip side, if we have a small within cluster sum of square distance, this would indicate that the data points are close together, close to the centroid. It's a sign that the cluster is well defined and compact. To get an overall within cluster sum of square distance for your k-means algorithm, you simply sum the within cluster sum of square distance values across all of the clusters. So that's how you get an overall total within cluster sum of square distance. And the goal here is to minimize this value. So to minimize the total within cluster sum of square distance during k-means algorithm to ensure that all the data points are as close as possible to their respective centroids. Okay. So as I just mentioned, someone had a great question. The k-means algorithm just starts by choosing the number of clusters denoted as k. So in this example, let's assume that we want to divide our data into 3 clusters. So k is 3. This is a key decision. It's a hyperparameter because k would determine how many groups the data will split into. So to begin, the k-means algorithm randomly assigns each data point into one of these 3 clusters randomly. At this stage, we don't know if the groupings make sense or not. This is an initial random assignment, so just a random start. So for our example here, we have 3. We have an orange circle represents data points assigned to the first cluster. We have a red triangle representing the data points assigned to a second cluster. And then we have a blue square representing data points assigned to the third cluster. Once again, these initial assignments don't reflect anything meaningful or any meaningful relationships within the data. They're simply this random start point for the next step within the algorithm. So now that we've randomly assigned our data points to clusters, what k-means algorithm does is it has this iterative process to improve these initial groupings. So the algorithm involves 2 key main steps, which are repeated until the cluster assignment can no longer be improved. So the first step is updating the centroid. So in this step, we basically compute the center for each of those clusters. So the center, once again, also known as the centroid, is calculated by taking the average of all the data points assigned to that particular cluster. So we find the mean of X and the mean of Y for all the data points within a particular cluster, and that becomes the new center or the centroid for that grouping. So in our example, the centroid would be all the data points representing the average flipper length and bill length, for example, for the orange circles or for the red triangles or for the blue squares. Step 2 is once we have this updated centroid, we move on to the step of reassigning each data point to the cluster that centroid is nearest to it. So this is similar to checking which basket of fruit belongs based on how similar the fruit is to this fruit that we defined as most typical within each basket. So the data points are then shifted from one cluster to another if they're closer to a different centroid. And this helps redefine the groupings. And these 2 steps are repeated. So the step of center updating and label updating are repeated over and over, each time adjusting clusters slightly until the assignments become stable. And what this means is that the data points are no longer changing cluster assignments and that the centroids stop moving around. So this iterative process is what helps the algorithm find the most meaningful groupings within the data. So returning to our penguin example, in the figure on the right, we see the first 3 iterations here. So as we discussed, k-mean follows this iterative process of either center updating and then label updating, where the data points are reassigned to the nearest cluster center, and then the centers themselves get updated. So by this third iteration, you can see that the cluster centers and the labels are remaining the same. And this tells the clustering process it's initialized and the algorithm basically has converged. So the algorithm terminates or stops when there's no more changes happening to the data point assignments or to the centers. So in our penguin example, this happens when the centroids stop moving around and the data points are no longer switching between cluster labels. Another really key indicator is the total within clusters sum of square distance. So once again, this value is the sum of the square distances between each data point and their cluster centers. So over time, this value will continue to decrease as the algorithm is refining its clustering. However, once the within cluster sum of square distance reaches its minimum, it will stop decreasing. And this means that the data points are as close as possible to their respective centroids and no further improvements are needed to be made. And it's at this point that the algorithm stops or concludes, and we're left with these final clusterings that we see here. And the process has effectively grouped all of the penguins based on their flipper length and bill rank. So once again, just to reiterate, k-means terminates when there's no more changes to the cluster data point assignment, and the total within cluster sum of square distance stops decreasing. Yeah, there's a hand up.
So this is not dependent on the visual inspection first. So what if we do the visual test first and we deliberately form the clusters based on the grouping itself? And is it going to affect the convergence and the speed of the model?
Are you asking the value of k that we choose?
No, so the value of k will be how many clusters we are forming, right?
Yeah.
But what if like randomly choosing the clusters, the data points in the clusters, we do the visual inspection first and we can see that there are already clusters which are forming. So rather than randomly choosing the points in the clusters, for example, I can see that the blue ones are forming the clusters or the orange ones are forming the clusters, say.
Yeah.
So
So
is it going
it's
to,
easy to see with just two variables, but when you go into multiple variables, this data inspection becomes more complex and you may not be able to visualize it as clear as this example was shown here, which is why we do things like k-means.
okay, thank you.
No problem. Yeah, I see another hand up.
Yeah, Julia. So my question is, I think it's maybe related also, but say,
Sure.
for example, in this one over here, we got the number three, right? Basically, you see three clusters. But
Yeah.
what would prevent the algorithm from even go lower into smaller clusters within the same cluster, say giving 6 or 8?
Yeah,
What?
so the value of k that you choose, similar to k in KNN algorithm, is a hyperparameter that you can choose. So we're going to go over how to basically loop through values of k and see the within cluster sum of square distance and talk about the elbow method just in a couple slides actually.
Okay, so the number three, we manually enter it, or is that generated automatically?
Like the value of k equals 3?
Yeah.
Yeah, we would choose that manually.
Got it. Okay, thanks.
Yeah, no problem. Yeah, so just to reiterate, the k and k-means represents the number of clusters we want to consider. This is a hyperparameter, so we would have to iterate through various values of k to identify which one is sort of the best. We're going to talk about how to do that in a little bit. Are there any other questions?
Yeah, so quick one. So what's the difference between the center updates and the label updates?
Yeah, so the center updates are referring to these big squares or circles or triangles. So these are representing the average within the cluster. So remember, the very first step is just random initialization, where data points are randomly assigned to one of the three clusters. From that, we calculate the average within the cluster. So the average within all of the blue squares, and then the average within all of the orange circles, and the average within all of the red triangles. Then the next step from that is we're seeing how close each data point is to the centers. And then we relabel the data points if they're closer to one center versus the other. So you can see, for example, this orange circle changes into a blue square because it's actually closer to this centroid rather than the orange circle. So that gets updated. And then once all these data points get updated, our center gets updated again. So we recalculate the average within this one, the average within the orange circles, and then the average within the red triangles. And we keep going iteratively until we conclude. Does that make sense?
So
Yes.
just
Yes.
yeah,
Okay.
just a quick question. But does it make sense to, I'm gonna just formulate this concept over here of having the ultimate centroid for the whole, all of these readings, and then based on the distance between each centroid with the absolute centroid, let me say, that we would be able to determine the number of iterations that we have, which is number 3. Can we, for example, if we put 4 or 5, it would give us higher WSSD for those centroids. Does that make any sense?
I'm not sure I'm following.
So say, for example, in one of these images, okay, what I
Yeah.
do is I create an absolute centroid. That is, I take into consideration all these features
All the data
regardless.
points.
And then exactly, and then say, for example, I take a point that is center to all. And
Okay.
then the iterations would be, well, let me say, determining the iterations is the distances between these smaller centroids for these clusters and the absolute or absolute centroid, which is in the center. So the smaller that value is, would help me determine the number of clusters that I can create. Know what I mean?
Yeah, I understand what you mean. I think I need a moment to wrap my head around that mathematically though. Um, I don't think that's common practice. So typically it just starts with a random assignment and then you build the centroids for each cluster based on that. I don't know how taking the mean across all the data points and then would,
And then, yeah, and then measure the distance between that, let me say, the absolute centroid, that's what I called
yeah,
it, and all these smaller clusters or centroids. Yeah, exactly. Just
yeah.
to find out that the mean, the smaller the mean, that I would reach the ultimate number K. You know what I mean? Rather than 3, it might be 4 or 5. Would that help as an additional dimension in the whole calculations? Maybe.
The number of iterations is also dependent on your random start, and I'm going to get into that in a second. So for example, this one here had a poor random start. So it needed more iterations, even though all the data points were the same. So I don't think that would necessarily be the case because these are all the same data points, just dependent on the random starts. They needed more iterations.
Mhm.
So maybe once I talk about this, maybe that'll make more sense.
Okay, cool.
Yep. So I already alluded to this. Oh, is there a hand up before I? Yeah,
Sorry, quick question.
yeah, sure.
So we just keep reiterating until the center update and the label update is same.
Yes.
Cool.
Yep.
Sorry, can you go back to the previous slide?
Yeah.
Okay.
Was there a question about the slide?
No, I just wanted to see this slide.
Oh, sure. Let me know if we're okay to continue. Okay. So we're going to talk about now what happens when in k-means, this is something that doesn't occur in classification or regression models. So in this particular algorithm, it can sometimes get stuck in something called a suboptimal solution. And this typically happens due to poor initialization. So remember with k-means, we're just starting with a random assignment of initial cluster centers. So if these centers are poorly placed, the algorithm may converge to a less than ideal solution that doesn't reflect the best possible clustering. So what I mean by that is in this figure here, you can see how k-means algorithm evolves over these first 4 iterations, starting from this poor initialization. So with each iteration, the algorithm adjusts the cluster center and then reassigns the data points just as we've seen before. But because of this poor initial start, the algorithm still doesn't reach the most optimal clustering by the end of the process. So we can see here that this process, it converged at 3 clusters still, just as we defined k equals 3. But this is not the most optimal clustering solution. So it grouped this cluster here into 2 groups rather than this being one, this being one, and this being one. And this is due to just the poor initialization as shown here in this first iteration. So you may be asking yourself, okay, that's not good. How do we deal with this? And one common strategy is to use random restarts. So this means running the k-means algorithm multiple times with different random initializations, and then choosing the solution with the lowest within cluster sum of square distance. And this would help us avoid getting stuck in these suboptimal clustering situations. So the key takeaway here is that poor clustering results from k-means can occur due to bad initializations. However, we can address this limitation by reinitializing the clusters multiple times and then choosing the result that had the smallest total within cluster sum of square distance. I'm just going to have a quick look at the chat. Okay, yeah, someone just asked about the random initialization. So what this is showing that, if you recall, the very first step of k-mean is to just randomly assign the data points to one of the 3 clusters. But due to bad initialization, we can see it randomly assigned, and then all the 3 centroids are really close. And as we go through this process of iterations, we end up with this suboptimal solution, where we know, for instance, that this should be one cluster, this should be one cluster, and this should be one cluster, but we don't get that due to this poor random start. And how we combat this is we do this k-means clustering multiple times with random initializations. And then we choose the output that had the lowest final total within cluster sum of square distance. And that's how we combat this issue. So we don't just do one random initialization, we run this multiple times. No problem. How do we know? So the k-means will stop, and that's when the models converge. So when we can't update the cluster centers anymore, and we can't update the data point assignments anymore, that's when it's converged. Yep, there's a hand up.
How do we know it's suboptimal if it's multiple dimensions that we can't visualize?
Yeah, so just to be safe, rather than we would do random restarts multiple times. So let's say 10 random restarts.
So this is like the equivalent of like doing random splits in supervised learning, kind of.
Kind of, yeah.
Okay, thanks.
Yeah, so you would do 10 random initializations and then choose the output that gave you the lowest total within cluster sum of square distance.
Okay, thank you.
Yep, no problem. Okay, so I talked about the fact that k is this hyperparameter. So in k-means algorithm, just like k and n, we're choosing the right number of k. In this case, k is referring to clusters. And this is really critical for good results. However, unlike classification tasks where we have this response variable and we can do stuff like cross-validation to measure the prediction error, k-means does not have a direct way of evaluating what the correct number of clusters is. So when k is too small, we often force our data points into distinct groups to merge into a single cluster. So this can result in a high total within cluster sum of square distance, as the clusters end up being far apart from the data, or the cluster centers end up being far apart from the data points that they're supposed to be representing. And the result is that the data isn't grouped meaningfully and our clusters don't reflect the true nature of the data. On the flip side, if we have our k being too large, we overcomplicate the clustering. So we start splitting the data into too many clusters, and this could reduce the within cluster sum of square distance. The reduction becomes significantly less after a certain point. And when we subdivide the data into these very small clusters, they may not provide any meaningful insight into our data. So once again, the goal here is to find the optimal value of k that balances between too small and we lose meaningful groupings, or too large and we overcomplicate the structure within our data. This is just a really nice figure to represent this. So here we see clustering results from various levels of k, ranging from 1 all the way up to 9. So this is k equals 1, k equals 2, etc., all the way up to k equals 9. And each cluster is represented by its center, and we observe how clusters evolve with each value increasing in k. So we see for k equals 1 that all data points are grouped into the single cluster, this would result in a really high within cluster sum of square distance, because the center is really far from the individual data points. We see in clusters 2 and 3 that as we increase k, we start to see the groupings into more meaningful clusters. We begin to capture the underlying structure within our data. In groups 4 to 6, or k4 to 6, the clustering continues to improve, but the changes now become sort of less noticeable. The total within clusters sum of square distance may decrease, but not as significantly as it has before. Then when we get from clusters k equals 7 to 9, at this point, adding more clusters really doesn't result in much improvement. And you can see that now the data is just over subdivided. So we see that after a certain point, adding more clusters may not improve the clustering quality, and we may start to overfit the data by splitting it into too many subgroupings, which is not ideal. So in order to choose the best number of clusters, we can plot the total within cluster sum of square distance on the y-axis for each value of k, which is shown on the x-axis. So as we increase the number of clusters, the total within cluster sum of square distance typically decreases because the data points obviously would become more grouped closer together. However, beyond a certain point, adding more clusters doesn't significantly improve the grouping. And this is where the elbow occurs. So here we see the elbow right here. And this is essentially where the reduction in within cluster sum of square distance starts to slow down. So before the elbow, adding more clusters led to this notable drop in total within cluster sum of square distance, meaning that the clusters are becoming more accurate. However, after this elbow, adding more clusters resulted only in a small improvement in total within cluster sum of square distance, and this indicates that the clusters are already pretty well defined at this point, and no further subdivisions are really necessary. So the optimal value of k at this elbow point here is where the within cluster sum of square distance reduction starts to slow down. So once again, this elbow point in the curve. And this is where we would achieve a good balance between the number of clusters and how well the data is grouped. So here we would pick the value of k equals 3. Okay, are there any questions? Let me just have a look at the chat. Yeah, so we use the elbow. I'm glad that answered your question, Omar. Can we compare within cluster sum of square distance between clusters to check whether we are at the optimal stage? What do you mean by at the optimal stage? Yeah, so you can also look at metrics that are beyond the scope of this module. But for example, things like silhouette widths that compare the difference in within cluster sum of square distance to between cluster sum of square distance to see how each grouping sort of clustered together compared to other clusters as well. But these, once again, these are more sophisticated methods beyond the scope of what we're going to be talking about today. No problem. Okay, it looks like all the other questions in the chat were answered. Okay, so that's all we have for the slide. So now that we have an understanding of what k-means clustering is doing and its sort of concepts, we're going to move on to the live coding portion of today's session using Jupyter Notebook. We're going to take 10 just as we typically do. So it's 6:50. We'll come back at 7 o'clock and then we'll hop into our live coding. Also, the pre-filled notebooks are available for you on the Git repo as well if you don't want to live code with me, though, as I've been saying, I always encourage it. Okay, so we'll come back at 7 o'clock. Hey everyone, so it's 7 o'clock, we'll get started again. So right before the break, I mentioned that the completed notebooks are available for you on the Git repo, but I always strongly encourage everyone to join me for live coding, just for more hands-on practice. And today in this session, we're going to continue working with the Palmer Penguins dataset that we were introduced to in the slides. So just as a reminder, this dataset contains two variables. So we have the penguin's flipper length and then bill length. And just as a first step, we're going to import our libraries as usual. I believe they were already actually posted in the chat, but I'm just going to repost it for anyone that might have missed it. Okay, so I'm going to just write a comment saying load in our libraries. Then we're going to load them in. Okay, great. So now we're going to configure scikit-learn to work well with pandas data frames. Just as we've done before, we're going to use the setconfig function. So we have setconfig, and we're asking it to transform our outputs into pandas data frames. Okay, perfect. So the next step now we're going to do is loading in our data. This should be review, sort of the same steps as we've been doing this entire time. So I'm going to make a comment just saying load in our data. I'm going to save it as the variable called penguins, and we're going to use the pandas read CSV function. I'm going to provide it with the path to where the data is. So it's under datasets, and it's called penguins.csv. So now when I call this object, we can have a look at our data set. So once again, 2 columns, bill length in millimeters and flipper length. So I'm just gonna now pull out the maximum and minimum values of these 2 variables just to see what we're working with in terms of range and whether or not we need to scale them. So I'm gonna have penguins, and then I'm gonna use the aggregate method. And then I'm going to pull out once again the minimum values as well as the maximum values so we get an idea of the range. So you notice that flipper length and bill length are on different scales. So for example, we have bill length ranges from 32.1 to roughly 59.6 millimeters, but flipper length ranges from 172 millimeters to 231. So this tells us that we should standardize our data before clustering just to ensure that all the features have equal impact on the distance calculation, preventing a single feature like flipper length in this scenario from having too much impact just due to its larger scale. So first, I'm just going to make a copy of our original data just so I don't accidentally overwrite it during pre-processing steps. So we're going to have penguins copy, and I'm just going to use the copy method. So penguins.copy. So now I've effectively created a copy of our data set. Next, we're going to use standard scalar. Just as a reminder, this adjusts our data so that each feature has a mean of 0 and a standard deviation of 1. And once again, this step is really important so features with larger scales like flipper length don't dominate the distance calculation during our analysis. So I'm going to create a scalar object from our standard scalar function, and then we're going to have to fit it to our data. So I'm going to create a new object called standardized penguins, and I'm going to fit transform our data. So penguins copy. So once again, now we're saving our standardized version of our data set as a new object called standardized penguins. So I'm just going to call it now so we can have a look. And now we can see that we've effectively standardized our columns so that they have, once again, a mean of 0 and standard deviation of 1. So now our data frame is clean, it's standardized, where all the features are on the same scale, so it's ready for our analysis. Okay, great. I also just want to quickly convert the standardized data set back into a pandas data frame just for ease when working with it with the subsequent modeling. So we're just going to make it into a pandas data frame. So we have our standardized penguins.
So what if we don't do this step? If we don't convert it into a data frame? Because when I did it, it doesn't make any it doesn't make any difference.
I think it might actually already be. Let me see. Yeah, it already is it's actually already a data frame, so we don't have to do
Yes,
this step. Yeah. Okay, so we can keep it as is. Okay. So now that we've standardized our data, we can visualize the relationship between bill length and flipper length just to see if we can detect subtypes or groupings within our data just through visualization. So I'm just going to copy and paste this into the chat for you guys. Okay. So based on the visualization, we can suspect that there's 3 groupings within our data. So we see one group that has, once again, smaller flipper length, smaller bill length. We see a second group that has smaller flipper length but larger bill length. And then we see this third group that has both larger flipper length and bill length. So as mentioned before, data visualization helps us see patterns within our data, but as the number of variables increase, this becomes harder to do just through visualization. So that's when we need more systematic ways to group our data, and this is when these clustering algorithms like k-means come into play. So now that our data has been inspected, it's been pre-processed, and it's been visualized, now we can start with our analysis. So our very first step is to initialize our k-means model. So a reminder, since k-means uses a random initialization, we need to set random state so that clustering will be reproducible. So k-means also has an n_init argument that specifies how many times the algorithm will run with different initial starts. So by running k-means multiple times and selecting the solution with the lowest within cluster sum of square distance, once again, we talked about the fact that this is allowing us to reduce the risk of ending up with a suboptimal solution through poor initialization. So I believe by default, this value is set to 10. Okay, so we have our k-means. We're going to use the k-means function, and we're going to specify just for now the number of clusters as, let's say, 5. And then we're going to specify the number of random starts as 10 and our random state, let's say, to 1, 2, 3. Once again, just because it has a random initialization, we're specifying a seed essentially so that we're able to reproduce this every time we run the cell block. We're also starting 10 random starts and we're specifying our value of k to be 5 for now. Okay. So now that we've initialized our model, we can fit it to our data. So keep in mind that we don't need to split our data into training and testing sets because clustering is an unsupervised method, meaning we don't have these predefined labels or a separate test set to evaluate its performance. So the goal here is really to group the data based on similarities rather than predict a specific outcome. So this is why we're not splitting into training and testing. Okay, so now we're going to fit our model to our data. I'm going to save it as an object called clusters, and we're using k-means.fit, and we're providing it with our data set that we've standardized above. Oh, great. So the k-means object contains valuable information that can help us visualize and evaluate the clusters. So to begin, we can create a scatter plot to show how the data points have been grouped. So first, we're going to assign the cluster labels to our data set. And we can do this by accessing the labels attribute from this k-means object. And this basically stores the cluster assignments for each data point. So what cluster each particular data point was assigned to. Okay, so we're going to create a copy of our standardized data frame once again, just so we don't overwrite the original. So we have standardized penguins with clustering now, or with clusters. I'm just going to create a copy. I see in the chat. Let me just double check and make sure everything's okay. Can you explain n_init again? Yeah, so we talked about the random starts and how we can fall into a suboptimal solution. So we're basically doing 10 different random starts just to avoid falling into the suboptimal solution because it takes out of the 10 repeats, it'll take the one with the lowest within cluster sum of square distance. Okay, some people are saying that k-means is known to have a memory leak. I'm not sure what that is. Is it giving you an error or a warning?
User warning.
Okay.
Yeah, it
I-
says user warning.
Yeah, I think if it's a warning, you can proceed. I've never seen that before. Yeah. I think for now it's okay. I can look into what it is, but I haven't had this come up before. So I'm not exactly sure what's referring to. Is this just a Windows problem, or is anyone with a Mac having this issue as well?
I believe it may just be a Windows problem because it specifically says there's a memory leak on Windows with MKL.
Oh, okay. Maybe I'll look into it after class, but I'm not sure what this is referring to. Okay, but because it's a warning and non-air, you should be able to continue. Okay, so as I mentioned, right now we're creating a copy of our data set. And what we're gonna do is we're gonna add the cluster labels that each data point was assigned to. So we have our standardized Penguin with clusters data frame that we created. I'm gonna create a new column called clusters or cluster. And once again, the clusters object that we've defined has an attribute called labels. So I'm just going to now append that. So now we have this new column with each of the penguins and their corresponding label that they were assigned. And now we can visualize the cluster. So we're going to create a scatter plot that shows each penguin's flipper length and bill length. And then each data point is going to be colored according to the cluster it belongs to. So I'm just going to copy and paste this into the chat. Okay. So once again, each data point now is color coded according to the cluster it belongs to, and you could immediately see how K-means algorithm has grouped the penguins. Okay, great. So now we've created our model, our K-means model, we visualized the results, but you might be wondering, okay, why did you choose K equals 5? Why 5 clusters? So far, this was just an arbitrary decision. It could have been any number. So we could have reran this with 2, 3, 4, etc. However, just as we did with KNN regression and KNN classification, when we determine the number of nearest neighbors, we need a method to choose the optimal number of K, in this case, number of clusters for K-means. So if you recall from the slides, we talked about within cluster sum of square distance representing how tightly packed data points are within each cluster around their centroid. And it helps us assess the quality of clustering by showing how close points are to the cluster centers. So to find the best number of clusters, we can use this elbow method, as we saw earlier, and this involves plotting the total within cluster sum of square distance on the y-axis by the number of different K values, and then we're looking for the point, the elbow, so where increasing K no longer leads to a significant reduction in total within cluster sum of square distance. So this, once again, this elbow point is what's going to help us determine the optimal value of K. Luckily, we don't need to calculate within cluster sum of square distance ourselves because scikit-learn makes this really easy for us. So when we fit our K-means model to the data, total within cluster sum of square distance is automatically computed and saved as an attribute called inertia within the K-means object. And this allows us to really quickly access the quality of the clustering for different values of K. So we can take a look at the total within cluster sum of square distance for the model that we just created. So for example, here we have clusters and then it's inertia. That's the attribute. And in this case, we have a value of 91.47. And what does this mean? Reminder tells us once again how tightly packed the data points in the clusters are grouped around their respective centers. So a low within cluster sum of square distance means that the clusters are more tightly compact with the data points close to the centers, and a higher within cluster sum of square distance indicates that the data points are more spread out and less tightly grouped. Let me just check the chat. These data points were randomly assigned to 5 clusters in the plot. No, so this is the final converged labeling. Yeah, and then there was another question asking how many iterations. So if you wanted to look at how many iterations were conducted to get to this final result, there's an attribute as well called, so you go back to your cluster model and it's n yeah. And this will tell us that there were 7 iterations in order for the model to converge. No, inertia is not a percentage. It's just the total within cluster sum of square distance. And you'll see it's hard to evaluate on its own, but you can see relative to other values of k where this 91 falls. Yeah, I see there's a hand up.
So what if like initially we took number of iterations to be 10, and here as we can see that it took only like 7 iterations to converge.
No, so this is the number of random starts. So if you remember,
Yes,
so that means we ran k-means 10 times with 10 different random starts.
yeah.
And
So
then
is it
it's
also
only
going to affect the result, the
No.
n in it?
So we ran k-means with k equals 5 10 times, and we only keep the lowest k-means, so the lowest total within cluster sum of square distance. So out of
Okay.
the 10 times we ran, we're only keeping one. And that one with the lowest within cluster sum of square distance concluded after 7 iterations. That's what this is saying.
Okay, but how did we choose number 10?
I would say 10 is typically the default. So the number of iterations, typically 10 is a safe, but you don't have to specify anything. If you did this, if you just took it out, I believe 10 is the default that it runs 10 times to avoid suboptimal solutions.
Okay, thank you.
No problem. I see there's another hand up.
Sorry.
No, go ahead.
Thank you. Okay. So we say that we have number of 7 iterations for the last, the final part.
Yeah.
But we don't know for the other 9 random iterations, we don't know how many iterations it's made, right?
No. Well, it's not really relevant. So here we ran 10 random initializations. We're only care about the one that gave us the lowest total within cluster sum of square distance. We don't really care about the other ones.
I see. But considering all possible combinations for each cluster, is it too small? After 7 iterations, it got the best results. So I thought it will make like thousands or hundreds of iterations to get.
No, I would say that's a fair, like you saw originally in the slides, how sometimes after 3 iterations the model converges and there's no more improvements either to the data points or to the centroid update. So it really just depends on the random start and how well the data points are fitting. Yeah.
I see. Okay, thank you.
Yeah, no problem.
If
The more
I
restarts you
use,
have, just in the chat, the more restarts you have, the more computationally expensive it is. So 10 is a good number. Yeah, you can continue. Sorry.
I was just going to ask, if I use the same starting parameter, should I be getting the same results?
What do you mean by same, like this?
the, yeah, those values.
Yeah, what are you getting? Like, are the colors different?
No, I realize, yeah, the colors are different, but I'm just saying even my inertia values is a little bit different and my iterations is 10.
We can up this. Like, let's say this might take a little bit longer to run. Let's see. Now I have 100 random starts and I'm picking the lowest from that. And my inertia value is the same. Yeah, my number of iterations is the same.
Okay.
Yeah.
But assuming we were using the same random
State.
state, it should
Yeah.
replicate identically, right? Like the results.
If not fairly similar, yeah.
Okay.
Yeah. I did notice sometimes that, for example, a random state, like if you're using a Windows and I'm using a Mac, for example, it's not a 1-to-1. I found that, especially in R, I've had
Okay.
issues with that. So it may be the case that we won't get exactly identical results, but it should be fairly similar.
Okay. Thanks.
No problem. Is it good practice to plot all the iteration steps to visually inspect? No, you would just have to plot I would just suggest plotting the final assignments. That's typically sufficient. Yeah, so the question about random state, yes, it's the equivalent of NumPy's random seed values. Yeah, and in terms of the inertia value, so inertia within cluster sum of square distance are synonyms essentially. So in how do you evaluate if it's good? On its own, we can't really get a good assessment of whether 91 is good or bad, but relative to the other values of K, we'll get different values of inertia, and then we'll see where that falls. Okay. So as I mentioned, to calculate the total within cluster sum of square distance for different values of K, luckily we can just perform a for loop and loop through several values of K-means all at once, and then we can store these values of total within cluster sum of square distance per each value of K, and then we can compare them. So our first step is just, I'm going to make a note saying compare different values of K. So our first step is just going to be to initialize an empty data frame. So I'm going to have penguins plus Ks. So that's what my data frame is going to be called. And I'm going to create a pandas data frame. And it's going to have two columns. So columns are going to be, one of them's going to be K, and then one of them's going to be WSSD, standing for within cluster sum of square distance. So this is my empty data frame so far. My next step is we want to loop through values of K. Let's say we want to loop through values of K from 1 to 10. To do this, we're going to use a for loop. And remember, we're going to use the range function that we talked about. So for K in range 1 to 11. So just to remember, the range function has the following arguments. The start argument, if we didn't put anything here, it would default to 0, but we can't have 0 cluster values, so it's going to be 1. And then we want to do values of 1 to 10. And the second stop value does not include 11, so it would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If we added an additional skip argument, we can skip the values, but if we don't, it'll just it would default to 1. So now we have for K in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then within the loop, we're going to perform K-means clustering for each value of K. So we're going to initialize the K-means with the current value of K, set the random state for reproducibility, and then we're going to initialize our model to the data set. And then we're going to fit it, to the data set. So we have our elbow K-means, that's just what I'm going to call it. And we're going to use the K-means function. The number of clusters is just going to refer to whatever K is. So K, once again, could be 1, 2, 3, all the way up to 10, depending where we are in the for loop. Our random state is going to be 1, 2, 3. I'm just going to specify n init as 10 for 10 random starts. Okay, so this is us initializing our K-means. And then after, we're going to fit it to our data. So K elbow dot fit, and I'm just going to provide it with the standardized penguins data set. So once again, we're fitting the initialized model to our data set within the loop. And then after we fit our model, we're going to concatenate the current value of K and its corresponding inertia value, or in other words, the total within cluster sum of square distance, to our data frame that we defined above, this empty data frame. So we're basically keeping track of K and its corresponding inertia values. Okay, so we have our current value of K. So I'm going to make a new data frame now, which is pandas, and then we're going to make a new data frame, and then I'm going to provide it with a dictionary. So the current value of K is referring to K, and then the WSSD column is going to refer to our inertia value. Inertia. Okay. And then I'm going to concatenate this data frame to the empty one that we defined above. So we have our penguins data frame Ks, and then we're gonna simply do pandas concat function, and we're gonna concatenate this data frame that we defined above. So the penguins clust Ks with our current value of K. Okay. And we're also gonna ignore index. So since we're constructing a data frame incrementally within the loop, we're just gonna specify ignore index is true when we're appending or concatenating, just to avoid any index related issues during the looping process. And this just ensures that the indices are 0 through 9, just without any gaps or duplicates, just making it cleaner for future operations like plotting that we're gonna do. Oh, do I have a typo somewhere? Oops. Okay. All right, so this is now what our data frame looks like. So we have values of K from 1 to 10, and we have the corresponding within cluster sum of square distance or inertia values. Does anyone, I'm just gonna copy and paste this into the chat. Does anyone have any questions about this? Can you please repeat the elbow block again? Yeah. So essentially what's happening here is the first step is we're defining an empty data frame with 2 columns. So it has K and within cluster sum of square distance, or WSSD. And then we're creating a for loop saying for every value of K in 1 to 10, what we want to do is first initialize our K-means model. And we're specifying the number of clusters as K. So this changes through each iteration of the loop. So n clusters first is going to be 1, then 2, then 3, etc. But everything else stays the same. So our random state's going to stay the same, and our number of random starts is going to stay the same. Once we initialize our model, we're then going to fit the model to the data. Then we're going to create a new data frame, just with the current values of K and inertia. Once we've done that, we're going to basically concatenate that data frame to the empty one that we defined above. So this is iteratively allowing us to build this data frame and concatenate on top of it so that the corresponding output looks something like this. Does that make sense? Yeah, so someone asked in the chat, if I have a big value of K, the inertia will be lower. So the more as you increase the number of clusters, the value of inertia or within cluster sum of square difference obviously is going to get smaller because there's more centroids and your data points are going to obviously become closer to the center. But at some point, this drastic difference between total within cluster sum of square distance becomes smaller. And that's this elbow point that we want to hone in on. So this allows us to hone in on the optimal value of K that's not overly simplistic or not overly complicated in parsing our data into too many subgroups. No problem. Okay, so to visualize how the total within cluster sum of square distance changes with the number of K, we can just plot it. So we're going to plot K on the x-axis and the inertia or within cluster sum of square distance on the x-axis, on the y-axis. And we're just gonna use a line plot to show where the elbow point is. So I'm just gonna paste this in the chat as well. Oh, I named it penguins with an S, so just replace these. I have an error somewhere. Oh, I think this line. Okay. Ignore the one I just pasted in the chat. Please use this one. Okay. So now we can see this elbow that I was talking about, where we see this really steep drop in total within cluster sum of square difference between K of 2 and K of 3, but this drop seems to subside after with corresponding increasing values of K. So this is sort of where our elbow point is. So we would choose K of 3. So we can see this clear elbow. And this indicates that increasing the number of clusters beyond 3 doesn't substantially reduce within cluster sum of square distance. Therefore, 3 would appear to be our optimal choice or our elbow, as it once again strikes this good balance between capturing the underlying structure of our data without overcomplicating and over subdividing the data points into unnecessary clusters. Does anyone have any questions about that? Yeah, Victor?
Yes, is there any specific way to calculate that value?
Unfortunately not. Still choosing the number of clusters is arbitrary. Like the elbow point is not like a mathematical like output. It's still something that you choose, unfortunately. So you can say you choose K equals 2 or K equals 4. Yeah, it's not as clear, I would say. Yeah, there's still some element of choice to it.
Okay, thanks.
Yeah, no problem. Okay, so just to sum up what we talked about in this notebook, we identified when it's necessary to scale the data before clustering just to ensure that all equal contributions of features. We implemented k-means clustering to group similar data points. We visualized the clustering results with scatter plots and highlighted groupings by color. We also applied the elbow method to determine the optimal number of clusters for plotting total within cluster sum of square distance by the value of K. So that's all for tonight in terms of new content. You can please feel free to play around with the live code. So you can experiment with rerunning k-means on different numbers of K if you like, in visualizing the results. So for example, if we scroll up and we can change the number of clusters here to 7, for example, and rerun the subsequent cell blocks. And we can see what it looks like even in terms of the scatter plot, how things change. So please feel free to play around with the live code. And also look at the pre-filled notebook available on the Git repo for more detailed descriptions with regards to each step. And yeah, that's about it for tonight. We ended a little bit early. So tomorrow and Saturday we have office hours or work period, sorry, for help with assignment 2. So once again, your assignment 1 and 2 are both coming up due soon. So if you need any assistance with that, the learning support will be here to help you with, once again, tomorrow and on Saturday. We also have office hours until 9 o'clock tonight as well, so please feel free to stick around. But if you don't have any questions, you're free to enjoy your evening. I'm just going to stop recording now.